here behave very nicely. They belong to one single mass parabola. And these high-lying ground states, they rain down by beta decays, beta plus, beta minus decays, till they reach the very bottom of this value of beta decay stability. But then, for the even nuclei, it is a bit more complicated because we have two mass parabolae, one for the odd nuclei and one for the even, separated by pairing interactions. It can happen that the bottom cannot be reached, let's say starting from zinc here. We are stagnated here at germanium, doesn't decay to arsenic here because of the energy conservation. But there is a way to reach selenium if you go from the first order to the second order in weak interactions. And this is the way one can somehow schematically show how it goes. So you have initially two neutrons here which convert to two protons via two ordinary beta decays with subsequent beta decays through the intermediate states through the intermediate states of this arsenic. So because this is a second order process, the half-life is rather long. So as you can see, these are the measured half-life actually in the underground experiment. So the half-life range from something like 10 to the 19 years to 10 to the 24 years. So they are really long if you consider that these, this unit here, which is a standard unit for double beta decay, is something like 10 billion times the age of the universe. So it is magnificent that such half-lives can be measured. So, and from the nuclear physics point of view, the situation looks like this. So we have two successive Ramoff-Teller decays through 1+ states of the intermediate nucleus, arsenic here in this case. And what we had to do, for the nuclear physicists, it remains to calculate the wave functions of these 1+ states. The more interesting thing, actually, which goes beyond the standard model of electroweak interactions, is this decay. It's a neutrino double beta decay. I should have said that the previous one was actually two neutrino case because in the final state you have two antineutrinos and always with two electrons. So in this case, we lose the two antineutrinos because now there's a propagator here where the initially created antineutrino is observed here as a neutrino in the second furnace. For that we need a Majorana neutrino. So a neutrino which is more or less equivalent to the antineutrino. So at the same time, of course, we lose two anti-leptons in the final state. It means that we have to break lepton number conservation by 2 units. And also we should somehow circumvent the helicity condition. So for that we need non-zero neutrino mass. And what we are interested in actually now, in this case, is this so-called effective mass, which is involved in the theory, which I will show soon. This contains now the mass eigenstates, which are the wanting ones, which we want to know. The CP phases we don't know, but these mixing matrix elements we know now, by now very accurately. So we can probe now, for example, the different mass hierarchies if this decay is detected and the half-life measured. I don't go into details. There is a claim that this has been already measured, but there's a small debate going on if this is a really good analysis of the decay and so on. But anyway, this is a very interesting decay which calls for theories beyond the standard model of electroweak interactions. And well, how does it look from the nuclear structure point of view? It looks a bit more complicated because now we go through all these intermediate states here. This can be seen in the following way. I mean, you have here this propagator, which is kind of neutrino exchange potential, which is kind of Coulomb potential here, and you can expand it in multiples. And these multiples now generate these virtual states here. For example, RPA calculations are using all these intermediate states. There are also, I mean, calculations like IPA2 and some shell model and those, which are using so-called closure approximation. And Jose Barea, the next speaker, may be addressing this in more detail, so I don't want to go into that business. So this is somehow the summary of double beta decay. We have the half-life here, or actually the decay rate here. It consists of this interesting quantity here, this effective neutrino mass, which we want to reveal somehow from the experiments, if there are any in the future. And then there's a standard, kind of standard phase space factor, which can be calculated more or less accurately. And the third speaker, Jenni Kotila, this session will address this more in detail. I'm interested now in this nuclear matrix element here, which is involved in the half-life. I don't, these details I leave because I don't have any time for that. But instead, now I go directly to the second topic, which is double beta minus decays. You may note here that, I mean, there are also some other types of decays, not only double beta minus decays, but some other decays, which I address later. So, I mean, this is actually I have two slides actually on this topic, and this is the first slide. Here I have I compare the Jyväskylä results with Franco's calculation, or his group's calculations, let's say. And these numbers come from this nice MEDEX workshop, which I recommend to everybody, which is so nice workshop every second year in Prague. And Franco was there already 2 times, yes, honoring us. Yes. So actually the local organizer said that it is a miracle that I could get you there. So, I mean, these are now the ground state transition and then decays to the first excited state. And as you can see, for these ground state decays, we more or less